In this paper, we present a novel 4D learning framework named LeaF. Learning frames for 4D point cloud sequence understanding. We have recently witnessed a surge of interest in understanding point cloud sequences in 4D. The data from human-object interaction, autonomous driving, and robot manipulation are naturally a 4D point cloud sequence. So, understanding such data for VR, AR and robotic systems is very important. We assume a 4D sequence comes from a single 3D scene with local dynamics. Here are two movable shapes from timestamp t1 to t+1. We can find their position and orientation changes obviously. So, let us think of a question. How can we depict the motion and understand the underlying complete geometry for each shape? For existing works, most of them treat the point cloud sequence as unstructured 4D data and exploit generic 4D learning methods without leveraging the prior that the whole 4D sequence just depicts a single 3D scene with dynamic objects. We place a camera to capture a single view of the shapes, then we can get some points from it. These points simulate the partial observation captured in real-world scenes. Since such methods do not take into account that 4D data are essentially continuous motions of 3D objects, it is difficult to maintain the complete geometry of the shapes and their motion trajectory based on these observations. We call this type of method frame-unaware spatial temporal convolution, which ignores the pose of each part. We propose to learn region-wise coordinate frames that transform together with the underlying geometry. Here we use a two-dimensional coordinate frame to represent the orientation of each shape. Similarly, we placed a camera to capture the data from a single view and got some points based on the occlusion relation. Based on these frames, we can rotate the observation points into the canonical space according to their orientation, which preserves their true complete geometry and decouples the motion information. In summary, we propose to learn frames for point cloud sequence. Upon obtaining the frames, we could easily align the geometry regardless of the underlying motion toward a more canonical and complete geometry understanding. The motion-agnostic geometric features also allow easier temporal association toward a better motion understanding. We provide an overview of our method. LeaF contains a frame learning module and a frame-guided 4D learning module. Given a point cloud sequence, we introduce a frame learning module to learn frames for each region. We design a frame-guided 4D convolution operator which can generate local and global features based on different frames at different scales. Given an input point cloud, we first apply data augmentation to obtain the augmented version of it. Then we feed both the original point cloud and the augmented one through the MS FrameNet and enforce their predictions to be consistent. Through various data augmentation strategies, we can keep the rotation equivariance of our predicted frames regardless of the time-dependent data corruptions. Here, we show the framework of the multi-scale FrameNet. Since geometric features are naturally multi-scale, the frames have to be multi-scale as well. We, therefore, propose to learn such frames through a multi-scale frame network. With the frame-aware 4D operation we can extract multi-scale region frame features, which are inherent representations of the underlying geometry but lacks motion information. So such region frame features are not enough to fully encode the 4D spatiotemporal information. On the other hand, the camera frame feature computed under the camera coordinate frame faithfully retain the motion information and can be a good complement to the region frame features. Here is an example of a camera frame and a region frame. We then propose to combine both features to obtain a more powerful and representative 4D feature. In particular, we design a two-tower framework to extract the region frame feature and camera frame feature. To fuse features from the two towers, we propose to use the region frame feature to guide the camera frame feature learning through an attention map that aligns the local region across different timestamps into a canonical space and allows easier temporal associations for better motion understanding. Finally, we can add different task heads to complete various 4D point cloud sequence understanding tasks. We cover 4D point cloud sequence understanding tasks: action segmentation on HOI 4D, action recognition on MSR Action 3D, indoor semantic segmentation on HOI 4D, and outdoor semantic segmentation on Cynthia 4D. We show that our method is able to outperform prior methods significantly. Here we show the results of the HOI 4D action segmentation and MSR Action 3D action recognition. And here we show the results of the HOI 4D semantic segmentation and Cynthia 4D semantic segmentation. We find that on the action segmentation task, our method without frame stabilization schemes results in a significant accuracy drop, and without learned frames or replacing learned frames with random frames and identity frames can both results accuracy drop. These ablation experiments verified each component of our method. Here we show some visualization frames. As can be seen, frames have both spatial and temporal consistency. Thanks for watching.